FAQs.
Yeah,
All
before
right.
we get started with these, we've got a few more questions that came in. So I think this is recorded for those that cannot stay through this, but these are some great questions. So I just want to go through a couple of these. One question, I noticed that my zero reading is drifting every time the load cell experiments temperature cycle, 170 degrees Celsius. Any comment to that?
That would not be typical unless it's in an assembly, which you could have some residual mechanical effects from that. If you have just a sensor sitting there and it's going through temperature cycles and the zero is changing, that's not typical behavior of a healthy load cell. Would you agree, Jacob?
Yes. I also would like to point out, so is it from like 0C to 170C, or is it 170C spread? Because if it's an aluminum load cell, it could be going above the rated
Operating range.
yeah, operating range. Uh, which basically the aluminum could be tempering and the material properties changing there.
Or gauges separating from the flexure, right? Yeah.
True.
So.
Yeah. Also, I think most of our standard product temperature range is up to 200 degrees. So that might be a time to, okay, up to 170.
Jaime, let's circle back after this. I'd like to know the model and get some more information, and we'll try to run that to ground. But no, it shouldn't be changing if it's again within the operating range. So, all right, we'll bounce through a couple of these FAQs. I think first one here.
Can I ask you a couple more questions
sure.
that came in through the chat? When installing a load cell on an actuator rod, does it matter the orientation of the load cell, meaning live end facing actuator body versus live end facing the test article?
I'll take it. Not significantly, but fundamentally, if you have the live end closer to your test article, you're going to have less inertial aspect, especially if it's cycling. So we would recommend that the live end is closest to what you are wanting to test, right? Because if you have that dead end with additional base and the cable, you could have some minor parasitic or inertial aspects impacting what your DOT is seeing versus what the sensor is reporting.
Another question is, how do you overcome crosstalk for multi-channel load cells?
Good question. So you try to optimize through the flexure design. There's going to be limitations, of course, and it kind of comes down to which is your primary axis of measurement. If you're talking an axial torsional cell, for example, and your axis, your axial load is much more important, then we would want to go with one of our 1216 models, which is starts as an LP, an axial load cell, and adds torsional bridges. If you're more concerned with the torsional bridge, then you'd want to start with one of our 5600s, which begins life as a 5400 reaction torque flange sensor, and then we add axial bridges to it. So typically the best thing to do if you're very concerned about crosstalk is to characterize it, right? Do some applied loading, see how it impacts the signal, and then adjust for it in your instrumentation. All right, we're going a bit long, I think, so let's get through some of these FAQs here, Jacob. I appreciate you guys sticking around with us. So which specification is most important when you evaluate load cell performance?
Yeah, I think it depends on the application and what the customer is looking for, right? A good place to start is SEB, but from there it can really depend on how much they are wanting to characterize on their end.
Yeah, so if you need a single specification, SEB is going to give you a good indicator of how accurate the load cell is. All right, how frequently should load cells be calibrated?
That's another good question. I think it depends on the use case again. It's definitely a good idea before a long extended test, or maybe a test where the load cell is going to be subjected to some pretty harsh conditions, to maybe get it calibrated before and after. And that can give you real good confidence for your readings during that test. But besides that, depends on the use case, anywhere from a year to when it needs to be.
Yeah, and we typically recommend tighter intervals as the load cells are newer. They get better with age and more stable with age. I'm talking very, very small amounts. So, typically customers would recal at least annual basis until they have, good confidence in repeated cals to say that they can be extended. We've done that in some of our standards, for example. We're able to extend them out a couple of years. So. What environments, applications can load cells be used for? Well, I'll answer that one. I guess pretty much anything. We've got, as mentioned, we've got vacuum rated for space. We've got load cells for oil and gas downhole applications that can be subjected to 30,000 psi with, a couple percent type air influence. So it really just depends. We can accommodate most environments and most applications as long as it's communicated and known up front.
So, Brian, what percent of capacity is the load cell accurate for?
Well, obviously up to calibrated range, 100%. Anything above that, it can start to deviate from that ideal linear output curve. And of course, if you get above 150%, you can start to cause some plastic damage to the bridge and permanent zero shift. So, and now as far as to how low can you go, of course, that gets asked a lot. We can provide certain calibrations that can give you lower load limit values. But a good rule of thumb in general is 10% and up. You should have high confidence in the specified cal values. If you need to go very low, have us calibrate at a low point. You'll have that data point. What are some of the common causes of failure, Jacob?
Yeah, mechanical overload is pretty common, kind of how you mentioned before, especially if there's some forces that are off axis that you weren't expecting. That can cause some combined loading that can lead to premature failure. Another one is like shock loads. Load cells are not really made to withstand shock loads, so it's really good to make sure that you're doing everything you can to avoid those.
Okay. Yeah, or if they have side loads that aren't expected, right? And all of a sudden the strain the bridge is seeing at full scale is a lot worse than maybe expected. So especially if it's high cycles, you've got to be extra careful there, fatigue type
Absolutely.
testing.
Yeah.
So when should you select overload protection, or when do you need it? Well, you want to answer?
Basically, a lot of the minis have overload protection, and there's a reason for that, right? It's very easy to overload them, even by hand, if there weren't those overload protection features in there. Brian, you have anything there?
Yeah, I mean, as capacity goes down, we typically try to offer it. Just it's necessary. But again, if you've got a test where you're interested in a certain cal range, very tight test range, but then it still needs to see quite a bit of extra mechanical overage, then yeah, overload protection would be good. We should mention too on our low profiles, we didn't touch on it earlier, even though we don't have any EDM features in the shear beam flexures, we can offer compression overload protection by tightly controlling the tolerances between the base and the bottom of the hub on the load cell. So our 1000 series, 1100, 1200, we can offer compression overload protection in the neighborhood of 300 or 400%, I think, through doing that. So again, we have some options there, but typically you can often handle this too with just how do you have it calibrated, right? You can always upsize the load cell capacity, ask for specific cal points, and now in theory, you still have confidence in the test range, but still have a much stronger load cell that can tolerate more mechanical load. All right, this is a good one. So how does the number of bridges improve your load cell performance?
Yeah, so if you have like a second axial bridge, that won't necessarily improve your performance, but it can give you some redundancy and a clean second signal. However, if you have a multi-axis, right, so you have another axis being measured, that can give you a lot more confidence in your readings, knowing how many other off-axis or moment loads are actually being applied.
Good. All right. Do you need to do a system level calibration with your instrumentation? So, all right. So we didn't get into too much detail when you start combining or start talking about different calibration options from a component to a system level standpoint. You've got the calibration of the load cell. You've got the calibration of your instrument. How accurately is it reading millivolt per volt, for example? If you're using TEDs, of course, it really becomes important as you swap out sensors. But typically, we would recommend in-rig system cals if you're concerned about total performance. That's going to take the load cell, the cable, and the instrument all as one system and report it all real time as units in rig in our CalRig. So it really comes down to how much precision do you need, and are you needing to swap out and change from different sensors to different instruments? If things stay paired as a system, then yeah, you can go ahead and get it calibrated that way and you keep that value. But as soon as you change out to a different sensor, there's really not as much value in doing a system level anymore, because now it really comes down to the component aspect. All right, what's the FOS of a load cell, Jacob?
Yeah, factor of safety. So that's going to be printed on our spec sheets. It's going to be the ultimate load. It's normally, I think for LPs, I think 300%. And that's when, right, the yield strength comes into play of the flexure of the spring. And if factor of safety is something that your application needs to hit a certain target or something like that, definitely reach out to our applications engineers. And we might want to derate a cell to get a little bit more overhead. That's relatively common. Then Brian, what makes a good load cell material?
Typical answer depends, right? Depends on the capacity,
Oh.
depends on the application, the environment. As long as it's communicated, we can pick the right choice. But I think in general, we talked about good load cell materials should have high stiffness, hardness, act like a good spring. That's the key thing. Otherwise, you're going to run into linearity and hysteresis challenges. So, all right, Jamie, I think you get to wrap this up.
Yeah, we got a lot of good questions there. Again, we'll have this reference material online, our YouTube channel and our website here in the next day or so. So keep track of that. We'll also be sending you an